Here we explain the next point, the vibrational energy levels and vibrational spectra for a diatomic molecule. Such a diatomic molecule can vibrate or oscillate as well as it also rotate. Such a molecule which acts as a two-body oscillator. For that two-body oscillator, we firstly find what is its frequency of the vibration, and then it is possible to find the energy, discrete energy levels for the explanation of the vibrational spectra. Such a diatomic molecule which having the two atoms of mass ammonium-2 connected by an elastic spring whose spring constant is K. If we assume initially the molecule gets vibrate along the x direction, means it performs the simple harmonic motion. Now how it executes the simple harmonic motion? The center of the two masses are vibrating in such a way that their center of mass remains fixed. That situation may be in absence of any external force. Such a vibrational frequency we firstly determining here. Before that, we know if a mass which is connected to spring and if spring which execute the simple harmonic motion, its natural frequency nu 0 is given by 1 divided by 2 pi under root k by m, where k is the spring constant. The similar case for the two-body oscillator, we find its frequency. Instead of m, we take the reduced mass for two-body oscillator. Therefore, the frequency we write nu 0 is equal to 1 divided by 2 pi under root k by nu, where k is the spring constant and nu is reduced mass. That reduced mass is m1 m2 divided by m1 plus m2. Now we find discrete energies for such a oscillator. Hence we use the theory one-dimensional simple harmonic oscillator. That problem solved with the help of the quantum mechanics. It gives the vibrational energy of the oscillator. That vibrational energy EV is equal to V plus half h nu 0. In that equation, nu 0 is the frequency of the oscillator that we have to write here. This is the, we say, one of the equation. Here V we call one of the quantum number. That quantum number is related to vibrational motion. Hence, V indicate vibrational quantum number and it takes the values 0, 1, 2, 3 and so on. For lowest quantum number V equal to 0, its corresponding energy is finite and that is the result of the quantum mechanics. That energy we call 0 point energy, that is half of h nu 0. All other energy states we call E1, E2, E3, E4 and so on. Before, if we substitute the value of nu 0 in that equation, we get EV equal to V plus half into h divided by 2 pi into under root k by nu. Except V plus half, all terms are constant. Hence, we write vibrational energy is directly proportional to V plus half. Now, how we represent the vibrational energy levels? We start from V equal to 0, 1, 2, 3, 4 and so on. And corresponding energy states are E1, E2, E3, E4. In that, energy is half h nu 0, 3 by 2 h nu 0, 5 by 2 h nu 0, 7 by 2 h nu 0. The separation between the two energy level is very small and it is found to be of the order of 10 raised to minus 1 electron volt or 0.1 electron volt. And separation remains constant since equispaced lines due to the separation between the two consecutive energy level is h nu 0. Hence, all energy levels shown here are equispaced. Now, that separation between the two level, as you know, also we know the vibrational energy is of the order of zero point 0.1 electron volt, and that energy is very larger than that of the thermal energy. Hence, we say that at the room temperature, if vibrational energy is larger than that of the thermal energy, all molecules must present in the lowest energy state, and that is lowest state is V equal to 0. Now then we explain vibrational spectra. Vibrational energy, that relation is known. From the potential energy curve, we also discuss about the vibrational spectra. Now, what it shows here, the variation of potential energy with nuclear separation R in case of the diatomic molecule. It shows the parabolic variation. The energy reaches minimum at particular equilibrium separation, and at that point energy is varied directly proportional to V plus half. Means all are equispaced near to the equilibrium position or the minimum energy region. But as the number increases, V increases, then what happens? The separation between the two lines, it goes on decreasing. This is due to the potential. We say that harmonic oscillator approximation is not valid as the shape of potential energy curve which deviate from the parabolic nature. Dotted line shows the parabolic variation of the potential energy curve near about the minimum energy. Only within that region, all vibrational energy levels are equispaced. After that, that vibrational energy spacing, it goes on decreasing with increasing V, since it deviates from the parabolic nature. Within equispaced vibrational energy level, there are number of rotational energy levels that is shown here. And when the transition can take place from vibrational, one of the rotational level in vibrational state to another rotational levels in next vibrational state. Now, what are that results? That results we discuss here. First result, we know the higher V values deviate from the parabolic nature. And that what happened? For that reason, the spacing between the vibrational energy level, it goes on decreasing as vibrational quantum number increases. Now, within these energy levels, the transition may occur. That transition may be absorption or emission of the radiation. Which transitions are spectroscopically allowed, that we decide from selection rule. Selection rule is delta V is equal to plus minus 1. Now, when it is plus 1, if the transition occur from lower to higher energy state, absorption region, and when it is minus, it is the emission of the radiation from higher to lower state. Such a, when the dipole moment of the natural frequency nu 0, it emits or absorbs that electromagnetic radiation of the same frequency. Hence, the energy change delta E between the two states, that is h nu 0, may be occur. The next point, we discuss the vibrational spectra. That vibrational spectra occur for only the particular molecules That molecule must be polar molecule. We call heteronuclear molecule, since the two molecules having different charge. And that molecule also changes its dipole moment. For example, which we see earlier, hydrogen chloride and other is carbon monoxide. These are the heteronuclear molecule. And the resulting spectra which always occur in infrared region. This is very important. Now, in the first lecture, we discussed rotational energy levels and rotational spectra. Here we know how the vibrational energy level arises and what is the resulting vibrational spectra. If we combine the two results together, we get the another spectra, vibrational rotational spectra. Means it also again shows that spectra which occur in diatomic molecule, heteronuclear diatomic molecule which possess permanent dipole moment. It also occur in near infrared region whose range is 1 micrometer to 100 micrometer and it is observed in absorption. The resulting spectra shows close spaced lines. Now how it shows close spaced line, that we discuss from the nature of the variation. Here we draw energy level diagram for vibrational rotation spectra. And we know the transition from different rotational levels of one of the vibrational level to the next rotational levels of another adjacent vibrational level can be occur. That means the transition occur from V equal to 0 to V equal to 1. In V equal to 0, there are number of rotational levels. Start from J equal to 0, 1, 2, 3 up to 4. From one of the rotational level, it transit to next rotational level in V equal to 1. Therefore, the resulting spectra which divided into two groups. Which are the two groups? One is on the lower frequency side and other is high frequency side. Now, which is on the lower frequency side? Now see, the same two regions we split up here. Some transitions which are spectroscopically not allowed. That transition, you know, it is the forbidden transition. Such a transition which we just draw it by the dotted line, J equal to 0 to J equal to 0, delta J is 0. It is not allowed. That means this is the natural spectral line, natural frequency nu 0, which split the two groups. First group is P group, P branch, and other is R branch. The selection rule for P branch and R branch is different, that we discuss here. For P branch, which is on the lower frequency side, delta V is plus 1, means only possibility is V equal to 0 to V equal to 1. What is the absorption of the radiation from lower to higher state? V equal to 0 to V equal to 1. Always it is positive. But the transition in rotational level can take place. Then delta J should be minus 1, in which case P branch. Now check it how it is get the delta J is minus 1, that is shown by the yellow lines. We start from J equal to 1 to J equal to 0. What is change in delta J? Minus 1. Similarly, the next level J equal to 2 to J equal to 1. 1 minus 2. Again delta J is minus 1. In that way, all equispaced lines we get on the low frequency region that we call P branch, and in that P branch the change in energy is constant, that is H divided by 4 pi square I, that we discuss here, and the transition in the rotational level start from J to J minus 1. The resulting branch is P branch. In that P branch, the frequency of the absorption of the radiation that is equal to nu is equal to nu 0 minus h divided by 4 pi square I into j, where j start from 1, 2, 3 and so on. Now for the other branch, that branch we call on higher frequency side. Selection rule for our branch is delta V is again plus 1, means transition is from V equal to 0 to V equal to 1, delta V is plus 1. Delta J is opposite to that of P branch, means it is minus plus 1. If it is plus 1 means the transition may occur from J rotational level in V equal to 0 to J plus 1 in V equal to 1, in such a way that delta J should be plus 1. For example, all that lines, equispaced lines, we draw by the red lines. J equal to 0 to J equal to 1. What is delta J? 1 minus 0, that is 1, plus 1. Similarly, the other line, J equal to 1 to J equal to 2. Difference is again 1, plus 1. Hence, such a spectral lines in the R branch, that line which possesses the frequency nu equal to nu 0 plus h divided by 4 pi square I into j plus 1, where j is equal to 0, 1, 2, 3 and so on. Equispaced lines we getting here. Spacing between P and R line is constant, and that constant is how much here? H into h divided by 4 pi square I. And the forbidden spectral line which we get at nu equal to nu 0, that we call band origin. In that way, we explain all the terms in rotational energy level and their spectra, as well as vibrational energy levels and their spectra, and both spectra combined together, it gives vibrational rotational spectra. Its results we discuss here in detail. In the next point, we discuss in detail about electronic spectra. Thank you.